Bismillahirrahmanirrahim. Let's continue our lesson on kinetic energy and the work-kinetic energy theorem. Let's consider a block, placed on a surface on the floor, and the block experiencing of F net to the right. This is a F net, summation of F. Alright. Initially, the block has V initial, and upon it reach delta X to the right, it's reached the V final. It has V final. So, to calculate work done by this net force on the block or object, we may calculate it by using integration of summation of F to the respect of dx from initial position up to the final position. So, this integration can be simplified in terms of applying Newton's second law, whereby we know that net force or sum of F is equivalent to MA. So here we go. We are substituting sum of F with MA. Right. Now we are going to open up the MA. The A itself is dV over dt. Right. And again, we are going to multiply this function with dx over dx. Dx over dt, is actually V, right? And we can simplify dx here. So finally, our equation are left with V and M. So instead of integrating MA or initially F, alright, now we are integrating the V because M is constant. So since we are integrating the V, of course the condition, from beginning to final must be also information about V. So finally, from this equation, now it becomes integration of MV to the respect of V, from V initial to V final. So if we integrate V here, we are going to have, V squared over 2. Right, then this is for V final. Let me show you. Integrating this one, you're going to have half M V squared with the condition of V initial up to V final. So now if you substitute the V initial and the V final condition here, you may have this pattern of equation. Work done by external forces or agent to the object is equivalent to half mv final squared minus half mv initial squared. We know that work done is a kind of energy. So when it's involving velocity or speed, we have a special name of it. We call it kinetic energy. This is actually the origin. How is the formula of kinetic energy is equivalent to half mv squared. So in simple manner, we can rephrase it or write it in terms of W external is equivalent to kinetic energy final, this one, minus kinetic energy initial, or equivalent to delta K. Alright, so what does that mean by this? It means that when work is done on a system and the only change in the system is in the speed of its members, the object, the net work done on the system equals the change in kinetic energy of the system. That is how we can conclude that, the work kinetic energy theorem. This is the theorem, or in terms of formula, this is it. Example 7.6. A block pulled on a frictionless surface. A 6 kilogram block initially at rest is pulled to the right along a frictionless horizontal surface by a constant horizontal force of magnitude 12 Newton. Find the block's speed after it has moved through a horizontal distance of 3.0 meter. So this is a situation. We have a block placed on the floor, right? Frictionless. Okay, so we have normal, we have weight, okay, and also this block is pulled to the right up to delta x displacement until it reach, okay, V final here, right? So we are going to apply work kinetic energy theorem. W external on the object, okay, is equivalent to delta K, or K final minus K initial, half mv final, squared minus 0. Why is it 0? Because the block start from rest. Okay, actually we may put it like this, but our V initial is 0. Okay, so the equation finally simplified in terms of this. So rearrange because we are interested in, okay, the V final. And then substitute the rest of the information. Your V final is 3.5 meter per second. Right. Suppose the magnitude of the force in this example is doubled. Okay, so now we have F prime. The 6 kilogram block accelerates to 3.5 meter per second due to this applied force while moving through a displacement delta x prime. How does the displacement delta x prime compare with the original displacement of delta x? Alright, so if we refer to this, delta x prime is less than delta x, right? Okay, W external. Okay, now when we have F prime, okay, we are going to calculate it by using F prime delta x prime. Mass equivalent to delta K, right? Okay, mass equivalent to F delta x. Because the delta K won't change, isn't it? Okay, then delta x prime is equivalent to, okay, make a ratio. Okay, A equals to B, B equals to C. So A also can equals to C. Then F over F prime delta x. Okay, now our F prime, given the information here, is doubled. So 2 times of F original. Right, then we are going to have half only. Cancel out this one. Okay, so half delta x. That is how we know that delta x prime is less than delta x. Concept to example 7.7. Does the ramp lessen the work required? Alright. A man wishes to load a refrigerator onto a truck using a ramp at angle of theta, as shown in figure. He claims that less work would be required to load the truck if the length L of the ramp were increased so that the angle would be smaller. Is his claim valid? So, actually, no, it is not valid. Why? Okay, let's take a look on this. W external on the refrigerator, our object, is equivalent to work done by the man plus work done by the gravity. How we know this? Because, okay, there always be weight at the center of the object. And the man is pushing, okay, the refrigerator upward like this. So we are considering no friction. Okay, so that is the only force acting on the refrigerator. So mass equivalent to 0. So now if we rearrange this equation, W by man is equivalent to negative of W by the gravity or weight. Okay, which is the weight is mg L, because The distance traveled by the refrigerator is the length of the ramp, which is L, right? So that is the displacement experienced by the refrigerator. So it's weight times L cos 90 plus theta. Why is it so? Because this is our refrigerator, this is our weight, the weight of the refrigerator, this is the L, the displacement. Okay, so the angle is this, which is 90 plus theta here, right? Okay, so it is equivalent to mg L sin theta, which is equivalent to mgh. So this is a proof that, okay, the claim is not valid. Okay, next subtopic is potential energy of a system. Right, let's take a look, okay, on this figure. We have a physics textbook, okay. We have F applied on it, which is upward, and we have weight of it downward, always to the center of the earth. The change in position experienced by this textbook is delta R. Okay. The work done by the agent on the book, Earth system, okay, is equivalent to mgy final minus mgy initial. This is our aim. We want to prove this one. Okay, so let's take a look. Okay, delta R must be y final minus y initial along J. Okay, W external, okay, is equivalent to F applied dot delta R. Right, so what is F applied? Must be equivalent to mg, because if we do sum of Fy equivalent to may, if it is constant speed, then ay is 0. So you have F applied, okay, minus weight equivalent to 0. So from here, F applied equivalent to weight. Then let's proceed. So F applied equivalent to weight, okay, and our delta R is y final minus y initial. So let's open up the bracket. Then we're going to have mgy final minus mgy initial. There is no more j. Why? Because we are doing dot product. J dot j equivalent to 1. I dot I equivalent to 1. K dot k equivalent to 1. Right, so from here, the W external is equivalent to mgy final minus mgy initial. This one proved. And from here, we can simplify the term, since W external is a kind of energy, okay, the energy related to the change in height of position, we call it potential energy due to the gravity, which is equivalent to, in simple, mgy. So from this, we may put it in simplest term, which is W external is equivalent to change in, okay, potential energy due to the gravity. Right. So still is the same story just now. Okay, gravitational potential energy depends only on vertical height of the object above surface of the earth. Okay, again, okay, because we don't have any delta x in this case. Right, so regardless whether the book is moved straight like this or the book is moved, okay, in, okay, this manner, right, doesn't matter, okay, whether it's moving applied by the applied force straight upward like this or in this way, okay, still the y initial and the y final is the same, right? So still we have delta U or mg y final minus mg y initial equivalent to W external. Right. So now example 7.8, a proud athlete and the sawtooth. A trophy being shown off by a careless athlete slips from the athlete's hand and drops on his foot. Choosing floor level as the y equivalent to 0, point of your coordinate system, estimate the change in gravitational potential energy of the trophy Earth system as the trophy falls. Repeat the calculation using the top of the athlete's head as the origin of the coordinate. In this example, we want to show you regardless of which point we refer to in terms of energy is still the same. So let's take a look. Assume M trophy more or less about 2 kilogram. The top of the foot is about 0.05 meter, let's say, above the floor. And the trophy falls from the height of, let's say, of 1.4 meter. Okay, so potential energy initial is mgy initial, which is equivalent to 27.4 joule. Potential energy final is equivalent to mgy final, which is equivalent to 0.98 joules. And change in potential energy due to the gravity must be, okay, U final minus U initial, which give you negative 26.4 joule, or more or less to negative 26 joules. What does that mean by negative here? You see here, it's fall down, isn't it? When it's fall down, the position, the height is reduced. So negative here, it means that in terms of potential energy, okay, the amount of it is reducing or losing, okay, because the height is decreasing. Right. Assume top of the athlete's head is 2 meter. Okay. So now let's calculate the U initial and U final. You will have this one, okay, as the Y initial of the trophy, and here is your Y final of your trophy, right? Then calculating delta U due to the gravity will give you negative sign. Don't drop it, okay? Carry it with your calculation throughout your calculation. It has meaning, it has its losing or decreasing. So you will have negative 26.4 joule or simply negative 26 joules. See, so regardless of the where is our setting axis or coordinate or origin of our coordinate, okay, still in terms of energy it's just the same. Right. Now elastic potential energy, okay, W external, okay, is equivalent to, within a mass spring system, okay, half kx final square minus half kx initial square. This is a recall, okay, and we know that potential energy in spring is equivalent to half kx square. So from here, right, okay, in terms of potential energy in spring, okay, is equivalent to change in delta US equivalent to W external. So this one, right? We can analyze from figure A up to figure E in terms of this applicable, okay? So this is the analysis of the elastic potential energy within a spring. Okay, take a look on this. Okay, before the spring is compressed, there is no energy in the spring block system. Zero. Energy bar here, everything zero. Okay, and the position of the spring is at equilibrium position. When the spring is partially compressed, okay, let's say we push the block against the spring and it's partially compressed. The total energy of the system is elastic potential energy. So we have, okay, the potential energy become more than half here. Okay, this is also the total energy of the system. Okay, the spring is compressed by maximum amount of X max. Okay, and the block is held steadily. Okay, so what happened in terms of energy? There is elastic potential energy in the system and no kinetic energy yet. In terms of energy is 100% because it's maximum. Okay, and this is also the total energy of the system. Right. After the block is released, okay, the elastic potential energy in the system decreases and the kinetic energy increases. Okay, because the block and the spring is in motion. So potential energy is decreasing, kinetic energy increasing, but okay, total energy stay the same. So if we add up the kinetic energy with the potential energy, it must be equal to the total energy of the system. After the block loses contact with the spring, the total energy of the system is kinetic energy only, because okay, only the block has motion right now. Potential energy in terms of spring, 0. How about potential energy in terms of gravity? Throughout the story here, do we have any change in height? No, right? So change in potential energy of the due to the gravity is not considered here because it's 0. Do we have potential energy due to the gravity? Yes, we do, because we are on the surface of the earth, isn't it? But the change of it, 0, because throughout the motion we don't have any change in terms of height. Okay, from the energy bar chart here, we also can transform the information in terms of graph of potential energy and also kinetic energy. Okay, this is position, and here we have okay, energy. For potential energy, okay, the shape of it, okay, U. Okay, kinetic energy, okay, this is the shape of kinetic energy, and at all the time, E total, okay, this is E total, consists of both. Okay, it's a constant value, right? So whereby we know that E total in mechanical energy is equivalent to kinetic energy plus potential energy. So at any instant, for example, at this point, at this position of X, okay, at this X, okay, we must figure out what is the value of the U plus what is the value of the K. That is the meaning of this equation.